Okay, this one's a tough one. We've got estimating the natural log of 0.75 using a Taylor polynomial about x equals 1. What is the least degree polynomial that assures an error smaller than 0.001? They provide a function that gives us the nth derivative of ln of x. All right. And that's good for n greater than or equal to 1. So first thing, we want to find out our maximum error, so we know we're going to have to use the n plus 1 term of the polynomial. So that structure is the n plus 1 derivative, right, at 1, our center, over n plus 1 factorial times x, right, which in this case is the value we're estimating, so that's our 0.75 minus 1 to the n plus 1. All right. Given this problem gave us a formula for the n derivative, we're going to rewrite that as a formula for the n plus 1 derivative by plugging n plus 1 in for each of the n's. So I have negative 1 to the n plus 1 minus 1, which is n, times n plus 1 minus 1, which is n factorial, over x to the n. And in this case, that x is 1. If we're evaluating it at the center. So we're going to start there. If we do have to use Lagrange error bound, we're going to have to come back and deal with that one and look at it at some other values. But we'll leave it here for now. All right, that's all going to be over n plus 1 factorial. And then we're going to multiply that all by negative 0.25 to the n plus 1. All right, now one more step of cleaning that up. We've got negative 1 to the n, and then I'm going to have n factorial on the top, but if I multiply by the reciprocal, I'm going to have an n plus 1 factorial in the bottom. So that's going to simplify to an n plus 1 in the bottom, and that's times negative 0.25 to the n plus 1. So I'm going to take a second and I'm just going to look at the signs of this, because if this alternates, we can use alternating series test. However, if it doesn't alternate, then we're going to be stuck, and we're going to have to use Lagrange error bound. So if I plug in 1, I'll note that the entire value of this is going to be negative for the first term, positive for the last piece, so we're going to end up with a negative. If I plug 2 in, well, the negative 1 piece becomes positive, the other piece becomes negative, so we have another negative term. As I keep plugging in higher and higher n values, you're going to see that every single term of this is negative. Now, since we're not alternating, we're going to have to use Lagrange error bound, which means that we're going to have to find the absolute value of the n plus 1 term. All right, but we're going to actually shift one little thing up, and we're going to find the n plus 1 derivative at some value z, right, instead of the center. All right, it might be the center, but it doesn't have to be. All right, and that's still going to be over n plus 1 factorial, and we're still going to multiply that by our negative 0.25 to the n plus 1. All right, because that's still going to be the value we're estimating minus the center. Now, the hard part about this is this f of the n plus 1 derivative at z. All right, what we have to do is we have to find z to maximize the n plus 1 derivative at that z value, where z is on the interval from the center to the point that we're estimating. So for us, that's between 0.75 and 1. All right, and again, we've got to find out what causes that derivative to be a maximum. All right, so we're going to step off to the side, and we're going to actually just focus in on the derivative for a second, which is this piece right here. All right, and we're going to consider that for z values. So we're going to look at its absolute values, and the negative 1 really doesn't matter. All right, so we're just focusing in on that piece. So we've got n factorial over z to the n. All right, because remember that 1 originally came from plugging the center's value in. So if I look at this expression for a z value of 1, I'd have n factorial over 1 to the n. All right, if I look at that piece for the other endpoint, 0.75, I'd have n factorial over 0.75 to the n. So I'm going to be dividing by a number that's less than 1, so that's going to force that to be bigger. Now, if we consider as we transition from 1 to 0.75, we're going to see that we would progressively create bigger and bigger numbers. Right? So this is actually where our largest value is going to occur. So I'm going to bring that value back in, right, and I'm going to use that value for the n plus 1 derivative at z. Right, so I've got n factorial over 0.75 to the n divided by n plus 1 factorial all times negative 0.25 to the n plus 1. Now, you realistically could have left off that negative if you wanted to, because the absolute value is going to clear it out anyway. So if I start pushing this together, I know that n factorial and the n plus 1 factorial on the bottom is going to reduce. I can put the 2.25 up in the top. So I have 0.25 to the n plus 1 over 0.75 to the n times an n plus 1. And that's going to take everything. Now, that's going to be a positive term, so I can leave the absolute value off if I want, and it's really not going to impact anything. All right, but this is the structure for our Lagrange error bound, right? And we need that to be less than 0.001. All right, at this point is when I'm going to lean in on technology a little bit. So I'm going to go to my graphing calculator. All right, and I'm going to go to, oops, didn't mean to make that full size. I'm going to go to y equals, and I'm going to type in my rule for the left-hand side of this as y1. So that's where I'm going to put in my 0.25 to the x plus 1 divided by, and then I've got my 0.75 to the x times x plus 1. And then in y2, I'm going to type in 0.001. So this gives me the two values that I'm comparing, and I want to find out when that y1 function is below. All right, so if I come in here, I'm going to go to Window. Realistically, I'm looking at really small y values, so I went ahead and went y values between 0 and 0.005. That gives me really a scale of 5 units from bottom to top on this, since we're really looking at 0.001. And then I looked at my answer choices of 3, 4, 5, and 6, and I figured 0 to 10 would be sufficient to see all those answers. So at this point, I'm going to hit Graph, and we get the two curves. Now, clearly, after we cross over that intersection point and move to the right of that, we're going to be below. So that's kind of our point where we're right at 0.001. So we want to find that, so we're going to go second, trace. We're going to choose intersect, which is 5. There's only one intersection point on the screen, so I'm just going to hit enter 3 times. All right, and it thought for a little bit, and it tells us 3.631. So 3.631. All right, and our n value needs to be greater than that for us to have a value that's less than 0.001. So I'm going to look for the first n value that's greater than 3.631, and that is 4. All right, that is our correct answer, and that's the choice that we'd want to pick. Most common answer that people give on this one is 3, and what happens if you did 3 is that you did not consider finding the highest value for the n plus 1 derivative over the interval from the center to the point we're estimating. All right, that work is the work that's the trickiest, and it's the one that usually hangs people up. And again, we had to do that because this is not an alternating series. So the correct answer is 4. That was a really tough one. Probably one of the longest videos you'll see me do to work through a whole problem. Hope that was helpful. Thanks again.